physics. And now you probably see where I'm coming from. One of my goals, is to teach the planet the necessary pure math and math physics to PhD 2, that's like second year classes, theory classes at PhD level, as well as M1 2, first year masters and second year masters, M1, M2. So 4 years, 4 levels of graduate education I will be teaching, starting with about a dozen preparatory, prerequisite if you like, undergrad courses, which I deem to be essential for the first year courses on the same topic. So this third course now is one of those undergrad courses, and it's the first in the theme of computer theory. Okay, and I estimate about a total of about 10% of all these courses in the deGarisMPC series will be of computer theory type. Okay, because the mathematical physicists will need to know some computer theory. They'll need to understand computers if they are to, for example, get jobs as experts in math physics, in topological quantum computing, to help teach this subject to computer science people and to math physics people. Now, the problem is, now I'll be blunt, the average intelligence level of computer science students is lower than the average intelligence level of students in pure mathematics and mathematical physics. Those latter two subjects are tougher, they're harder, they're more intellectually demanding, more abstract and so forth. So as computer science becomes progressively more math physics based, and I see that as inevitable, why? I see it as a consequence of Moore's law. Gordon Moore noticed in the mid-60s that the number of transistors you could cram onto a chip was doubling every year and a half or so, and that phenomenon, that trend, has been labelled Moore's law ever since, and it's been valid now for, God, half a century pretty well. So so the size now, with each doubling, the number of transistors you can put onto a chip today is I think more or less like 10 billion, something like that, some huge amount. And the way Moore's law is achieved, essentially, is by making everything smaller. You just cram in more transistors per square centimetre. Now, the smaller things get, sooner or later, they will become of atomic and molecular scale, right? And that means that their behaviour will be subject to the laws of quantum mechanics, in other words, physics, math and physics. Now, topological quantum computing requires a knowledge of topological quantum field theory, TQFT. Now that is hard stuff. It's harder than master's level, it's PhD level. So to understand that, to understand topological quantum computers, which in time will become strategically, economically important, and therefore the politicians, the leaders of countries, will push that these topics be taught. So that means that computer science students and math physics students will need to understand TQC, topological quantum computing. And to know that, you need to understand topological quantum fields. To understand what topological quantum fields are, you need to know what quantum field theory is. Now QFT, that can be taught at master's level, and I'll be doing that. And to understand quantum field theory, you need to understand what ordinary quantum mechanics is at, say, first year master's level and undergrad level. Now I've just pretty well finished in my second course, that was at undergrad level, that was a course on quantum mechanics. So I will be teaching at 5 levels. Undergrad level, preliminary or prerequisite courses, about a dozen or so of them, and then M1 level, first year masters, M2 level, PhD 1 level, and PhD 2 level, so five levels. And if I can stay alive long enough, I'm mid-60s now, retired for 2 years. If I keep doing this, and it requires discipline because it's relentless. You're just churning out YouTube videos every day. You have to absorb the material, write it up on the whiteboard, film it, and then process the film, and then upload it to YouTube. So it takes a huge amount of time, and it's unforgiving. It's just every day. It's relentless. So I had breaks occasionally just to stay sane. But if I can continue that for decades, there will be hundreds of courses done, and I'll be able to cover all these bases, all these 5 levels, and then I can do repeats. In other words, the same topic at the same level, but by a different author using a different text to get a different take, a different perspective on the same topic. But that's years away. At the moment, I need to just do what I call the core courses, the basic ones, the fundamental courses first, higher priority courses first, and then I can do repeats. All right. Well, let me start then on the actual lecture. Now, if you've not seen the format that I use, I have a rather large whiteboard here. Its length is 2.4 meters, and its height this way I think is 1.4, maybe 1.2. I'm not quite sure. Maybe. Well, anyway, large, and I divided it up into quarters. So this would be 1 quarter, so this is the upper left quarter, and then the second quarter would be, well, this one below it. I've camera angled so that you only see 1 quarter at a time. You'll never see, unless I specifically choose to do it, but you'll never see the whole board at once. So one board is 4 quarters. A quarter I call a session. The amount of time for filming is a session. And so this is session 1 of the first lecture. So lecture 0, part A. And I usually split a session, usually 2 or 3 parts. Okay, so why computer theory? Because the math physics guys who are following these courses, going up to know what topological quantum computing is, stuff like that, they will need to know more computer science. And I'm hoping some computer science guys will get more interested in math and physics, because that's the future of computing, right? So as future computing becomes more math, pure math and math physics based, its general status level will go up. Why? Because the subject will become more difficult. Why? Because pure math and math physics are the most difficult topics on campus. In general, you go to a good university, the brightest guys on campus will be the professors in pure mathematics and mathematical physics. For example, in the US, the average theoretical physics professor has an IQ of 170. So, a very bright crowd of people indeed. Okay, and they're the guys who will make probably. We're talking about the future, so it can't be certain. But probably they are the guys who will make quantum computing a practical and hence economic reality. And when that comes, for the reasons I said before, when computers become 2 to the power n times, in other words exponentially, more powerful than today's classical computers, then that's just going to not just revolutionise computer science, but all of science, our whole economy, our technology, everything, because we can simulate nature then. Right, so these math physics guys need to know more computing. Now, there's probably, now given this is undergrad level, well, sort of a mix. It's sort of merging senior level and M1 level. Now, the earlier chapters of the text are definitely easier than the later chapters. There are several chapters which are more advanced topics of the earlier chapters, and they are definitely M1 level, right? Graduate level. So, you know, parts of the course get quite a bit harder than the undergrady earlier chapters. So it's a senior M1 mix level course. Okay. Now, some of you may just be interested in that per se, and you don't really care about the higher math physics stuff. You're just not interested in that. You're just following it specifically for this course, and that's fine. You know, I'm expecting a mixed audience, so probably all kinds of different motives why you're watching, why you're following this course. Maybe you're a computer scientist who, for some reason, just never did the theory of computation, and you're curious to know about, you know, what's the theory behind computers, stuff like that. Yeah, maybe so. You'll get a lot of theory, because, you know, that's what it's about, computer theory. In this course, it'll be a long course, as I was saying, maybe 3-4 months, given 400 pages of text. It'll take a while. Right. Okay, so let's get into the nitty-gritty of the first session. A long text, you know, about over 400 pages. It's principally in 3 parts. After the introduction, so this the lecture 0 is effectively, oh, by the way, 1 lecture, 1 chapter, 1 chapter, 1 lecture. They map 1 to 1. So this is lecture 0, like preparatory, or the chapter that gives you the tools and the notations and so on that you will need later for the 3 main parts. So if you want keywords for the 3 main parts, automata, computability, and complexity. They're sort of like keywords, the 3 main themes that run through the course, the text. Automata, I won't try to explain what they are today, but in this lecture, but speaking generally, they are the tools, the means by which you compute. They are the computers, the things that compute, that calculate, if you like, right? And computability, that's a study of what you can compute. Some things you cannot compute. Some things you can show mathematically. That's what this is about, the theory of it. You can prove mathematically that certain things cannot, underlined, not be computed by computers, by machine